I did my sophomore project on a Kayak Speedometer. Here's my system diagram. As you can see, you move this way in the kayak and the airflow is moving this way, and here's your anemometer or speedometer that measures the airflow and then can tell you how fast you're going. Background. Here's some different types of anemometers. This is a cup anemometer, which measures it by cupping the wind. A windmill anemometer, which you probably already know what a windmill is. And then a plate anemometer, which is one of the earliest types of anemometers that reflects the wind. These, although they're great anemometers, would not work on a kayak, for they are too bulky and too big. So I chose to do a solid state transistor anemometer. This was my first attempt, the first circuit. It didn't work. I had it all built, but the circuit was really touchy and would randomly drop to 0.7 volts and it wouldn't work. And even with extreme heat, the transistors are supposed to detect heat and it was not working properly. So I moved to this different circuit. This is my second attempt. Here we have a 9-volt input instead of a 5-volt. Instead of using a traditional ground, we have a nominal ground using this LED. And instead of using an LED, I use 3 transistors in series, or I'm sorry, 3 diodes in series. And a couple of the resistor values differ, but the transistors, I use a 2N222, and the op amps stay the same, using an LM358. So how it works. This op amp right here is connected between a potentiometer and this transistor, and it basically works like a bridge circuit. So these 2 transistors are on one side, and these 2 resistors and potentiometer are on the other side, and the op amp just records the difference between the 2 and amplifies it and sends it back to this transistor. This transistor was pulled away from the circuit to detect heat more. And as it cools down from the wind, the op amp sends it more current to keep it hot so it can keep detecting the voltage. So parts used, I used 2N2222 transistors. I originally started with this plastic casing, but switched to the metal to detect the temperature better. I used an LM358. It originally called for a TS462, but since we didn't have one in stock, I used an equivalent dual op amp with the same pinout. And like I said, I used 3 diodes instead of the LED for the nominal ground. Some of the findings. Once I turned, you can't really see it in this picture, but I had a fan here on this transistor. And once you turn the fan on, it takes about 10 to 15 seconds for the circuit to turn fully on and for it to start working. Here you can see, I'll go to the waveforms, it might be easier. You can see right here, nothing, this is when we turn the fan on. And you can see this spike right here is the circuit turning on. And then the voltage going up the more that the fan is on. And this one just shows that as soon as it reaches peak voltage, I turn the fan off, and you can see the voltage going down when we turn the fan off. So, of course, after I took the waveforms, the circuit stopped working. But these were the voltages that I recorded. I measured at pin 2, 3, and 1, and you can see the voltages are pretty much the same with the fan off and with the fan on. There wasn't too much of a change. So, add-ons. These little pieces were added on to the transistors to help detect the wind it helped conduct the airspeed more. And right here, I didn't get a chance to add this on, but this was the converter that took the voltage and it would convert it to a miles per hour, so you could actually read how fast you're going. And this was a fan I used on the transistor. Questions? Comments? Yeah.
So why did you use the 3 diodes instead of the 1 LED?
Well, if we go back to the circuit, we needed a -2 volts here, and if you put 3 diodes, -7, -7, -7, and I basically add up to -2 volts. So it was just an easier way, instead of having an LED, you could put just 3 diodes.
The waveform shot,
Yeah.
what is that the voltage of? Can you go back to the circuit and show where you made that measurement?
That would be the output of 1, I believe, going back into the base. That's showing the voltage. And you can see it giving more voltage. Yeah.
So the whole thing is based off of the transistor cooling down as the wind blows,
Yes.
right?
Yes.
Is there anything keeping normal wind from affecting it?
No, and that's one of the questions I had when doing this, because what if it was a windy day? You know, I guess it's one of the downfalls of using this type of anemometer.
Or would it be any different with a cup anemometer?
I guess not. I mean, all anemometers work on wind, so.
So, yeah, I mean, I think we spoke about it a little bit, other than putting paddle wheels in the water or something, there's really no other way to sort of measure.
How fast you're going in a kayak, right?
So,
Jordan?
So what was the digital display for at the end that you were showing?
That converts the voltage from pin 1, and it takes the output voltage that you're getting, and it was supposed to convert it into a miles per hour, so you could read how fast you were going. It was just a display, so you could.
Yeah.
I had it on and working. I just didn't have time to add it to the circuit.
what, we looked for a while at that R4 resistor, the 22 ohm one. What was important about that? Do you remember?
That was okay, so I'm pretty sure that was where, I don't remember. There was so much going on with this circuit.
Yeah. I seem to remember that's where we actually made the measurements of those waveforms, but,
That could have been it. I thought it was pin 1, the output, but we did a lot of different measurements in different places, so it very well could have been.
so we didn't get much on the second op amp, the A2 op amp. We didn't really look at it. I mean, that's where they're taking.
Well, it's the same chip, just different outputs.
Yeah, but that's where their meter goes at the output of the second op amp. I think what we discovered was that output didn't change very much, and we had better results looking at R4.
Yeah, this page.
Because you had a calculation of current there, right there.
Yeah, right here. So
Right,
the current through the 22 ohm.
so, and I think when you did it with no wind and with wind when the circuit was still working, that current changed a considerable amount. It went from like 20 milliamps to 120 or something like that. And then the circuit stopped working.
Yeah. It's a really touchy circuit.
Okay, any other questions? All right, thank you.
Yes.
To improve the accuracy of this, could you modify it to maybe work in water, so then if you have a headwind coming at you, it's not going to affect the
Oh yeah, that could be something, to put something in the water and then measure like the water flow through. I think that would be a lot more accurate.
It's more of a comment than a question, but I think they use something like that on ships. I'm not 100% sure, but I think that they use a small, like, prop-driven speedometer.
Yeah, something that goes in the
Yeah, it's
water.
not necessarily a paddle wheel, but it's like a small impeller that they use, I think.
It's definitely something that can be improved upon with this.
Yeah, the big advantage of this, I think, was it was gonna be small,
Right.
battery operated and, you know.
You know, and given more time, I would look into a battery pack, preferably like a solar powered something, so you could take it with you and it would be waterproof. Anything else? Thanks, guys.